So now we would continue talking about the MIMO systems. And in the last videos, we saw the MIMO system model. And we saw that if you have multiple antennas at the transmitting end and multiple antennas at the receiving end, your system model for a MIMO would look like this. That if you have for each antenna at the transmitting side, that would be connected to all of the receiving antennas. And the channel gain between the ith receiving antenna and the jth transmitting antenna is given by hij. And then we can formulate all of this into the matrix form. And you can see that this becomes a equation y is equals to hx plus n. So that is what we saw. That is the system model for the MIMO, and then we make use of the singular value decomposition to convert this channel with all sorts of interferences into a number of parallel channels. So your system model is that your state signal y would be equals to the channel matrix H times X plus N. The N is your noise, additive white Gaussian noise. And then we said that, for example, if we have this as a system model, that is, if we have a channel, if X is input to this channel, then it would output Y, which is nothing but Hx plus N. So this would be output would be Y, Y1, Y2, YMR. And now we can make use of something at the transmitting end, something at the receiving end. That means we can process the signals at the transmitting and the receiving end in a manner such that we can convert this channel matrix into, into a set of parallel channels. So remember we said that this H can be decomposed using singular value decomposition into U sigma V Hermitian, where we said that both U and V are unitary matrices. That means their columns, which by the way would be the eigen vectors corresponding to H Hermitian and H Hermitian H respectively, and they would be orthonormal to each other because these are unitary matrices, and their Hermitian is also their inverse. So these were the properties of the unitary matrices that we discussed last time as well. So then we said that if we can pre-code this signal, the signal that we want to transmit it at the transmitting end, such that your transmit signal is pre-coded by a matrix V. That means if X tilde is the input, X empty tilde, then before transmitting, just pre-code it in a manner, and that gives you an X vector. Remember, this is a V matrix, and this V matrix is the same V matrix which we got from the channel decomposition. So that means if you want to pre-code in this manner, you have to have the channel sign information at the transmitting end. So if that is the case, this is called the transmit pre-coding. And then at the receiving side, what you can do is you can reshape your signal. So you see the signal y, which is nothing but h, which is u sigma v Hermitian times x plus n. Remember, h can be given as u sigma v Hermitian, and x is v times x tilde, where x tilde is the signal to be transmitted. Then at the receiving end, we said that if we reshape our signal at the receiving end such that your y tilde is equals to u Hermitian times y, then effectively you would have a set of parallel channels. If we reshape this at the receiving end, using U Hermitian times Y, and that gives us Y tilde. One tilde, this is Y two tilde, YMR tilde, where U is a matrix of dimension MR cross MR, and V is a matrix of dimension, the MT cross MT. So if we apply this to this H, to this Y, your Y tilde that you would get would be U Hermitian times U sigma V Hermitian, V times X tilde, plus U Hermitian times your N. And this, we said this would be an identity matrix. This would be an identity matrix. And effectively, what you would get, Y tilde would be sigma times X tilde plus this N tilde, which is nothing but U Hermitian times N. Remember, U is a unitary matrix, and hence all of its columns are have a unit norm, and they are orthonormal to each other. So because of this reason, the variance of the noise would not be different after this transformation. Although it would get rotated because of the matrix U, but the rotation, the noise is, this rotation would have no impact on the noise because we assume the noise to be circularly symmetric noise. So the distribution of this noise would remain the same even after this transformation, and the fact that U Hermitian is a unitary matrix. So that is your Y. And then we said that because this sigma is nothing but a this sigma is nothing but a diagonal matrix, you have diagonalized your channel effectively. So this sigma, depending upon the dimensions of the number of transmitting antennas and the number of the receiving antennas, this sigma matrix would be either a fat matrix or a skinny matrix, but nevertheless you have RH number of parallel channels, where RH is the rank of the channel matrix, which is equals to, if it is full rank, it would be equals to minimum of MT, MR. So effectively, so you will have this Y, this sigma would be a matrix comprising of the singular values, sigma 1, sigma 2, sigma MT, and for the let's assume that MT is equals to MR and all zeros. So this would be your sigma matrix, and hence your channel, which was MIMO channel, has now been changed, can be represented as that you would transmit this x1 tilde that would get multiplied with sigma 1. You would add noise n1 tilde in it, and you would receive y1 tilde here. Similarly, you would have x2 tilde. You would multiply with sigma 2 here. Noise would get added in 2 tilde, and you would get y2 tilde here. Right? And this, you would have RH of these kind of a channels, where RH is the rank of this. So if XRH tilde, let's multiply with sigma RH plus NRH tilde, that will give you YRH tilde. So effectively, your channel gets you have converted your MIMO channel into a parallel channel. So that was parallel decomposition of the MIMO channel, and that we discussed last time. So in today's video, we would talk about the beam forming. So we have talked about the multiplexing gain here. So now we will talk about the beam forming for the MIMO channel.